Look at how a surgeon operated in the 17th century. The tools were rudimentary, the anatomical knowledge basic. A professional mastered a small, static set of skills and repeated them. Compare that static, historical environment to a modern, highly dynamic air traffic control screen. Today, performing a job requires what cognitive scientists call adaptive expertise, the fluid coordination of highly integrated knowledge, skills, and attitudes to navigate entirely novel situations. Whether it is an air traffic controller, an emergency room doctor, or a logistics manager, professionals must continuously evaluate dozens of simultaneous data points and take immediate action under intense pressure. They cannot rely on a simple linear checklist. They have to continuously adapt to a shifting set of variables. Because the nature of professional work has evolved into complex, dynamic coordination, the architectural models used to train these professionals must adapt accordingly. For decades, the default approach to training has been atomistic design. This method breaks a complex domain down into a linear sequence of isolated learning objectives, dealing with them one by one. This creates strict compartmentalization. It separates declarative knowledge from procedural skills and attitudes, treating them as if they operate independently in the real world. The inevitable result of this process is severe fragmentation. Learners are taught individual subskills in a vacuum, completely removed from the context where those skills actually need to be applied. This atomistic method leads directly to a persistent failure in education, known as the transfer paradox. This data chart compares two distinct training models. To get a learner to master specific, isolated objectives quickly, instructional designers often use blocked practice, practicing error 1 repeatedly, then error 2, and so on. In the short term, this minimizes time on task and cognitive effort. But when learners face unexpected real-world complexities, when an unknown variable appears, the knowledge built through blocked practice collapses. They cannot coordinate those isolated skills to solve a novel problem. Atomistic design sacrifices operational readiness for perceived training efficiency. Holistic frameworks like 4CID provide the path to reliable transfer. The four-component instructional design architecture, or 4CID model, is built on four interdependent elements. The first component is the learning task. Instead of starting with isolated facts, learners are confronted with authentic, whole-task experiences from day one. This requires them to use knowledge, skills, and attitudes together immediately. To prevent whole tasks from overwhelming a novice, the model organizes them into simple to complex task classes. A task class simplifies the learning environment by limiting the number of interacting elements the learner has to manage. However, the task remains conceptually whole. Within each of these task classes, the design requires strict variability of practice. By forcing learners to navigate scenarios that differ on multiple dimensions, like changing environments or varying client constraints, they learn to abstract information away from the specific details of a single task. This whole task backbone forces the integration of constituent skills. It creates a realistic cognitive anchor that learners can attach new information to. Complex real-world work always contains non-recurrent aspects. These are the elements that require problem-solving, clinical reasoning, or decision-making in unpredictable situations. To support these non-recurrent aspects, the model introduces its second component, supportive information. This layer provides the mental models and cognitive strategies necessary to bridge the gap between a learner's prior knowledge and the demands of the current task class. It explains the theoretical why behind the domain's organization and how problems within it should be approached. The strict design rule for supportive information is that it remains non-intrusive but constantly available to learners while they work within a specific task class. By architecting this continuous layer of support, designers ensure learners can logically reason their way through novel problems, rather than resorting to blind guessing. Not every part of a complex task requires deep reasoning. There are also recurrent, routine aspects that must be performed identically every single time, regardless of the scenario. For these rigid routines, the model uses Component 3, procedural information. These are the exact step-by-step instructions for executing specific actions, and they are injected directly into the execution of the learning task. Unlike supportive information, which is always available for reference, procedural information is delivered exactly just in time during the task execution. As the learner gains expertise within the task class, this procedural guidance is rapidly faded. Just-in-time procedural information quickly prevents cognitive overload. It gives learners the exact behavioral scripts they need at the precise moment of execution and removes them the moment they achieve competence. Certain routine subskills require a massive degree of absolute automaticity to be performed safely and accurately under pressure. If these highly recurrent subskills are not fully automated, they drain critical working memory capacity, resources that the learner desperately needs for higher-level strategic reasoning. To build this level of automaticity, the model employs its fourth component, part-task practice. This is the space for highly repetitive drilling of specific actions. The absolute rule of holistic instructional design is that this isolated practice never precedes the whole task. Drill work only begins after the routine aspect is fully contextualized within a meaningful, whole-task environment. They must understand how the specific skill fits into the larger picture. By delaying isolated drills until after a holistic context is established, designers forge rigid, reliable automaticity without accidentally triggering the transfer paradox. This schematic represents the fully finalized blueprint of the 4CID model. This architecture succeeds because it maps its structure directly to two distinct mechanisms of human cognition simultaneously. The first mechanism is schema-based processing. The highly variable, whole-task practice on the left side of the blueprint forces the brain to construct generalized cognitive schemas. These schemas allow the learner to solve problems in unfamiliar situations. The second mechanism is rule-based processing. The isolated, repetitive practice on the right side of the blueprint builds rigid cognitive and psychomotor rules, guaranteeing that routine actions happen automatically. These two fundamentally different learning processes are orchestrated to run concurrently, building deep understanding and rapid execution without interfering with one another. This orchestrated dual processing is the direct solution to overcoming the transfer paradox, ensuring learners can perform familiar routines efficiently while adapting to completely new challenges. The 4CID architecture moves beyond standard curriculum writing, offering a rigorous framework to engineer training environments for adaptive expertise.